Today is Cassandra Lunch 51. I know we've been doing this for more than a year, but next week will be the 1 year. Well, we've been doing it for 52 weeks. So it's kind of a big milestone. We never thought that we'd be going this long in the age of COVID. And I think halfway through, we decided that we're just going to continue doing it. Even as people start to go back to offices and have physical meetups, I think this is something we're going to continue doing because this is a perfect time for people to attend from West Coast in the US, East Coast here in the US, people in the UK, Europe area, as well as some late nighters in India. Unfortunately, we can't manage the Australians just yet, but maybe we'll have another meetup time for those guys on the other hemisphere. Today's topic is Cassandra cluster architecture. This is different from Cassandra internal architecture, which is very, very fascinating. Trust me. Sorry, I'm not even showing my face. Very, very fascinating. In fact, I would say Cassandra is one of the easiest databases to really wrap your mind around and understand how and why it works. Way more, I think, elegant. Well, I don't know if it's elegant. It's just simpler. Simpler for very, very vast use cases. I've volunteered Arpit and Josh as co-organizers here because they've been filling in for me when life has gotten busy. So Arpit and Josh, if you guys feel like it, put your mug shots there. I didn't want to randomly catch one off of Zoom. But Arpit and Josh, thanks for co-organizing, and Elena, thanks for recording and producing the meetup videos. Always looking for people to help, not just as organizers, but as speakers. So if you have something you want to talk about related to Cassandra, we'd love to have you. We're part of a much larger community of data practitioners called Data Community DC, which includes 10, 12, I don't know, sometimes it's more. There's even blockchain DC, which I don't even have on here right now. But generally data related District of Columbia, commonly also known as DC2. We covered Cassandra protocol. DataStax is a Cassandra variant. There are other variants of Cassandra. And if it uses CQL, if it uses Cassandra native protocol, we're talking about it. Don't see, oh yeah, I do see somebody. Ankit, did you want to just say hi? Normally at this time, we ask people to just introduce themselves if they're kind of new to our group.
Hi everyone, hi Rahul. This is Ankita. Okay. I have been, no problem. I've been working with Cassandra and NoSQL databases for about 4 years now. And I recently came across your sessions. I don't know why and how I have missed it for so long. I just came across it yesterday, and I felt I really need to attend these sessions more regularly. And it was very informative. So hi everyone, and I further hope to contribute probably one day for these sessions.
Great. Would love to have you share some of your experience on this. Thank you. Appreciate it. I think everybody else kind of regulars here. Group rules, if you have a question, you can just ask it. Just be polite. You can use it also not to just ask a question, but to expand on something the speaker is talking about. Some speakers may say, please put it in chat. I would prefer that you just ask because I'm not looking at the chat. Our company, Anant, is a sponsor for this meetup. We help professionals and our clients build platforms at scale and run big operations. Specifically, we focus on Spark, Cassandra, and Kafka. DataStax is a partner and a sponsor. GW University locally. I think after June, everything is opening up, so probably going to start having some in-person events back in their campus. Well, and we'll live stream that too, so it's not like we're going to stop doing that. We have some local sponsors. Reach out to them to start getting them to have some venues for us as well. And of course, I'd like to thank all of our organizational sponsors at the data community DC level. Data community DC is a nonprofit, and so these donors help with the year-long programming and to meet the gap of any funding for any meetups that we have in our group. Anyone have any announcements, jobs, meetups, hackathons? Let's see if there's any mention here. Yeah, so we're always looking to hire people, part-time or full-time, and you can check out careers.anant.us. Upcoming events next week, looking at Airflow and Cassandra for cluster management. We also have another sister meetup on Mondays called Data Engineers Lunch, and we're going to be looking at Akka actors for data processing. And then the following Cassandra Lunch will be using Airflow and Spark for ETL in Cassandra. Our videos are all on YouTube. And we also publish the best neutral Apache Cassandra knowledge base in the world, where we link to things related to Skilla, to DataStax, to Gigabyte, to Cosmos, and normally about 4 or 5 links a week. And it's actually featured as one of the columns on the DataStax developer newsletter. So it's pretty good. And with that, I will transition to today's topic. So today we're going to talk about Cassandra cluster design and architecture. And specifically, we're talking about how to use the Cassandra data centers to manage workloads or to isolate workloads. And the reason I put this deck together is even people that have a lot of experience with Cassandra that have been only working in either a single data center cluster or multiple clusters, but they're all single data centers, they don't quite understand the benefit of having the idea of a data center. And there's various benefits. And so that's what I would like to do, is go through some fundamentals of cluster architecture and then discuss different workloads and why they would make sense in a multi-data center approach. We also have data centers for physical distribution of data. We'll talk about how that can be used for strategic advantage for companies and for redundancy. There have been several topics in the last year that we've covered in terms of how to talk to Cassandra, Akka, Spark, APIs, and we'll tie that in as well on how they fall into the larger scope of cluster design. So some basics, you've seen this slide probably a million times, but it packs a punch, so we're going to use it again. Cassandra is not for tiny data, right? So if you need fast reads and writes of terabytes of data, yes, okay, cool. We continue using Cassandra. Do you need replication and availability around the world? No, then maybe don't need Cassandra, but we can talk about potentially if you want to have a multi-workload. And so that replication and availability, while some other workload is happening, is, I wouldn't say it's availability on the world, but it's availability even when other operations are happening on that data. We'll talk about that in a second. And does a database never have to go down? If so, then Cassandra is probably the right one, if you do it right. Don't use Cassandra if you have gigabytes of data, right? Your application can have like one data center and it works fine. And if your system can have maintenance windows to go down for 4 hours, you probably don't need Cassandra for that. You can manage with other databases, relational and non-relational. But definitely don't use Cassandra if you want to be cool. That is not a prerequisite. And I say this in jest, but reality is there's on the Cassandra, Apache Cassandra mailing list and in Slack, people have some really asinine use cases for Cassandra, and I don't even bother getting into the conversation because I know they didn't think twice about why they needed it. And well, I shouldn't be so mean, but yeah, don't use Cassandra if you're trying to be cool. It's really not for simple use cases. It's for, rather, I would say it's not for tiny use cases. It's not for medium-sized use cases. It's for big data and big and fast data. That's what Cassandra is useful for. And we have done some comparisons with Cassandra with other databases, but today let's just focus on how do we use this idea of a data center for managing workloads. So in this picture right here, we see one cluster with 2 data centers, DC1, DC2. And we'll come back to this when we talk about replication in a second. And this picture right here, it shows a globally distributed cluster, which has essentially a data center in each continent that has people on it and distributes data around the world. And so if you're a global company and you need to have data distributed around the world, Cassandra would be useful for that. What I like to tell people is that Cassandra is like a Dropbox for structured business data, right? So if you have a computer and you put some files in it, it syncs it up to Dropbox. And if you have a mobile device, it syncs it down from Dropbox, right? But that's like more of a hub and spoke. Whereas in Cassandra, you don't need to have anything that you connect to. You can have 2 data centers that are constantly replicating data back and forth. If data is written to North America, it synchronizes, if configured, across all data centers, or maybe just 2 data centers. And if data is written to, let's say, Australia, and Australia is doing some data reads and writes, and North America is doing some reads and writes, all of the data can be then replicated across the world. Okay. I might actually draw it out on the whiteboard of what that could look like, but why would we do that? Right nowadays, with data protection requirements, people don't want data leaving Europe. Why would you want to do that? Well, there's some use cases where it could be useful while still maintaining data privacy laws. Quick recap of the data model, and we're going to talk about key spaces in terms of the physical data center. So it's good to understand how the data is organized. So ultimately, under the hood, Cassandra stores data as key values, and those key values are organized by rows, and those rows are organized by partitions, and those partitions are in a table or a column family. Nowadays, we just call them tables. And those tables exist in a key space, okay? And a key space generally is the single unit of collected data that could be replicated once or twice in one data center or in multiple data centers, right? So when we talk about data centers and replicating data, we're talking about replicating data at the key space level. Inside the key space, inside the table, if we say in a particular data center that we want it to be replicated 3 times, then the partitions get replicated 3 times in that data center, and they get distributed out, and they're kept intact. Each partition is kept intact. But as a collection of tables, if you want it to be across the world, we're really talking about key space replication. The tables look a lot like relational databases. When you do a CQL query, which is a subset of SQL, it looks a lot like a table, but it's not. You could be doing a query and getting 100 rows, and those 100 rows could be stored in a partition. Or you could be doing a query that's going across 100 partitions. Okay? But just remember that when we're talking about a key space, it's a set of tables, and those tables have partitions, and those partitions have rows. And those partitions are replicated as many times as you want. But that's all defined at the key space level, right? Replication factor is defined at the key space level, not at the cluster level. So just a review of kind of like logical versus physical data centers. And I've put the same line in both, which is clusters have data centers. So you can have a cluster that is physically distributed, right? And those data centers have racks. Racks are used to manage availability zones. So if you're using Cassandra on the cloud and you're in US East 1 physical data center at Amazon, or US East, whatever, at Azure, then if you have 3 availability zones, A, B, and C, in that region, you could say rack 1 is in AZ1 or AZA, rack 2 is in AZB, and rack 3 is in AZ3. And what that will do is when we say replicate the data 3 times in just that one data center, you can still have availability and redundancy in one data center. Okay. Now racks have the nodes themselves. Okay, and the nodes have data. So we'll have some, we'll recap. We'll come back to this in a second. The important thing to note about physical data centers is you can still have really high levels of availability and redundancy with availability zones in the cloud if you use racks, okay, without having to have separate data centers. All right. Some people actually use racks for physical separation, right? So physically and on-premise, they'll have a physical rack, a cabinet of, let's say, 50 machines, and another physical rack with 50 machines, and another physical rack with 50 machines, right? So we would say this machine has rack 1, this machine has rack 2 defined in the configuration, and the data will be distributed equally amongst all 3 of those. And I've even seen a scenario with a cluster which is like 1,000 or 1,500 nodes, where the racks were actually 3 physical buildings in the same office campus. Right? So even if one building lost power, there were 2 complete sets of data in 2 different buildings. So just, with physical data centers, you can have physical separation of data using racks and data centers. And what I mean by physical, again, not just in the physical world, but also in the cloud, everything is physical, right? So I want a data center on US East and I want a data center on US West. We probably would not have racks going across it, right? We just want 2 different data centers. What are logical data centers? So logical data centers are defined the same way as physical data centers. It's just the machines they just happen to be in the same place. Why would you want to do that? That's what we're going to talk about today. Data centers have key spaces. As I mentioned earlier, key spaces have tables. Tables have partitions. Partitions have rows. Partitions are replicated in a given data center as defined by the key space. Okay. So what do we get in terms of single versus multiple data centers? So let's talk about availability and performance. If we have a single data center cluster, we get availability in the sense that partitions are replicated in replicas per data center, right, as configured in a key space. And in this case, it would just be one key space. So we can have the data replicated 3 times in a particular data center. And it's available because if one node is down, the other 2 replicas are available. Performance, sure. If one is busy, it can get data from another one. Data is managed via, we would call, global consistency, quorum, one, all, and you can have serial. So this consistency level, because we don't have 2 data centers, these are the consistency levels we can use. When we have multiple data centers, we have a couple of other consistency levels, right? Local quorum versus quorum. The data is repaired across the replicas here, right? Nothing complicated, works fine. What do we get when we have a multi-DC cluster? Well, we get to manage data slightly differently. If we have 2 data centers, let's say there's a user that is uploading their TikTok messages or tweets or Instagram messages, and they're in the California region, right? Their data could be written with local one or local quorum to just that data center, because that would be fast, right? They'll be able to get the data and say, yeah, I got the data, everything is good. But there are times in which we want to have a global consistency, even in multiple data centers. So when we're talking about stock or e-commerce, if somebody's about to buy something, and even though they're accessing the website from California, if somebody in New York buys some product, right, the next time that person goes to buy it, like we don't want to wait for that data to trickle over and synchronize. So we can set global consistency levels even with multiple data centers. All the consistency level at global means everywhere, right? And local means just at the data center. And unfortunately, I don't know of a way to do local quorum on 2 data centers out of 5, let's say, other than making, anyways, that's a question somebody asked me, and I don't know the answer to that. Maybe somebody knows the answer to that. And then the repair process, right? It not only has to sync the data across replicas, but it has to do it in each data center. Because repair is making sure all the data is consistent if it was missed somewhere along the line. Okay. So having multiple data centers, you don't lose performance at the data center level. You actually gain it because you can have one region talking to, let's say, New York talking to US East and California talking to US West, and the traffic could be different in US West. So you can scale that data center separately. You can keep adding nodes to that data center separately than to rather add it to both, right? So having multiple data centers gives you the ability to scale the different physical areas separately. What do we get in terms of reliability and redundancy? Well, the full data set for a key space and all the tables in it are distributed amongst nodes in a cluster in a data center. The racks can help evenly distribute it. The racks, as I mentioned, can be put into availability zones in the cloud or physical rack. So that gives you some redundancy for reliability. In a multi-DC data center, the full data set for a key space and table on all the tables inside it are replicated to wherever you want it. So you can say my catalog key space is replicated 3 times in US West and 3 times in US East. Yeah. Or you could say, I want my California users key space to only be in US West, because most of the data centers in the US West are inside California. Because California has its own data protection regulation now, right? And so that data would not replicate to New York. Same thing with if you have a European data center, you could say European users only exist, that data only resides in Europe. Same cluster, different data centers, you're just telling it where to go. So you can tell it to put key space in 1 data center 3 times, or 2 data centers 3 times in each. That creates 6 replicas globally. So data centers can also be put into physically different locations, right? So as we've been talking about, but they can also be put into logical workloads. So you can have 1 data center in California for, let's say, transactions, right? Real-time reads and writes, millions of whatever transactions per second. And you can have another data center in California that is used for analytics, meaning while the data is being bombarded on the primary data center, you can have another data center, I shouldn't say primary, a transactional data center. The analytical data center is replicating that data in real time. And you could be doing some machine learning on that, writing the data back to that data center, and then that data would get replicated back to the transactional data center. So now we're touching upon 2 different types of uses of the data center terminology. One is physical isolation, physical distribution of data, and the other is workload isolation or workload separation. Here's an example of a multiple workload with a logical separation, right? So yeah, imagine that we have a cluster with 3 data centers, and the green nodes, regardless of whether it's a container or not, don't worry about it. Imagine that these are 3 virtual machines in, let's say, US East, right? And then these are 3 virtual machines in US East as well. And the data is being replicated across the data center. And all of these other data centers could also be in US East, okay? But the operations with Akka and Spring and Node are only happening to this data center. And that does not impact the work that could be happening on a machine learning data center, right? Where we have Spark running. And it could also be separated from the Presto workload, which is to do reads of this data and do its own work. Presto has its own processes that it runs on. So dependent on how many people or how many transactions are coming, we could scale this data center separately, whereas leaving the reporting data center and the analytics data center because it's the same workload. It's not increasing. Okay. So this is a way to do logical separation. Okay. You can also do this as physical separation, where you don't really differentiate the workloads. It's just in 3 different places. So as you could do that in virtual machines, you could also do that with containers. It doesn't really matter, right? Cassandra is a JVM binary. It works off of TCP/IP and disk. Those things happen to run equally well, or equally in terms of functionality. Disk, memory, CPU, and network, right? They're all available whether you're in a container or a virtual machine or physically. But let's just say nowadays people are using Kubernetes. You can have pods of Cassandra co-located with pods of Spark in one kind of pool, while as another pool is used for APIs, another pool is used for reporting. Here's an example of hybrid or multi-cloud data centers, right? Physical separation, same cluster. As long as you have the networking open, you can have a data center on AWS, Azure, and Google Cloud, constantly replicating data. So if one day Bezos does not want to have cheap servers, just hikes the price up, we can just turn these off and still be fine, not be affected. Or if US East, which is in Vienna, close to where we are in DC, that old data center goes down, which it has in the past, everything's fine. We have other data centers in the cloud that have the same data. You can also have data centers on premise synchronizing with data centers in the cloud. Why would we want to do that? Well, hardware is not cheap. Just because you pay for it per use doesn't make it cheap. So you may want to have heavy processing for analytics on premise, because you just need bigger, like really, really massive machines. Or you may want to have cold storage of data, right? Certain key spaces here, whereas other more lightweight key spaces would be here. But all of that could be replicated down, and you can do analytics on it. Right? So you can have data sets kind of separated by data center, but all of them getting replicated here, and you can do your massive processing here. Okay. The other benefit of having something like this is, let's say Black Friday comes along and you have an e-commerce application. You can just go to your Terraform's, I love Terraform. You can go to your Terraform state file and say, I want to make this 30 nodes, and I want to make this 90 nodes, and I want to make this another 90 nodes, right? And as this thing scales up and joins the nodes, Cassandra will replicate that data, right? And after Black Friday and Cyber Monday are done, we can scale those down, and you still have the same on-premise cluster, not being affected by that traffic, but rather the data is coming in. It's just not being bombarded by reads and writes. It's just data is getting trickled in at its own pace. Now, you can also have a multi-planet data center. We're not quite there yet, but the same concept applies, right? If you're still working 15, 20 years from now, regardless of whether we have people living on Mars, there's enough of a momentum in the world now with people traveling that there's the interspace network, which is basically what connects, I don't think it's the exact name, but what connects all the satellites, right? It's possible, as long as it runs TCP/IP, right, on IP version 6 or IP version 4, Cassandra can do the same thing it's doing at an interplanetary scale as it does on a planetary scale and as it does on a national or regional scale. And so why would this work? This would work because you have transactions happening independently in these data centers. And since the writes are, they're reconciled by last write wins, eventually this data gets consistent. Now, I know that there's a speed of light problem where there's going to be a little bit of a gap, but important records, right? If we wanted to have it as an interplanetary society, if we want to have records across the world and across the planets, Cassandra would not be a bad choice, because it would just magically work at an interplanetary scale. So let's say we're using Spark. right? Everybody knows that Spark is an awesome tool and it works great, does anything you want at scale from a computational perspective. Nowadays, from a machine learning perspective, it connects with a lot of different databases, including Cassandra. The thing with Spark is, unless you have indices on your tables, unless you have indices that are backing your table in Cassandra, the way Spark filters the data, it just goes, reads the data and filters it in memory. So it has to get the data first. It can't filter it if it doesn't have the data. So if you imagine there's a lot of traffic that's happening in a data center, let's say that's supporting commerce or some business critical or mission critical operation, and you start to do a table scan, even if you're doing it with Spark, it's not healthy. It's going to put pressure on the cluster, right? So commonly, we will use Spark against one data center, whereas the other data center is used for OLTP, right? So OLAP with Spark, OLTP, but Cassandra is in both data centers, right? So here's an example where, you see Cassandra here, right? So data is getting landed here somehow. Spark is then reading it and then writing it back into Cassandra. This Spark streaming process could be heavy, and we don't want that to affect the user. Well, that data can be replicated to another data center, right? And you can do Spark SQL queries on it and not affect the other data center. And it's not just limited to Spark, right? You can have Akka writing to Cassandra in one data center and then having Spark read it from another data center. Here's an example of leveraging ETL, right? How does this affect users? So you don't see Cassandra here, okay? But if you're having a Spark process that is gathering data, oh no, it's here, sorry, gathering data, and it's dumping it into Cassandra, and that ETL process takes up a lot of memory and CPU, and you want the reports to be fast for users, well, you can have another data center. You can have one data center for ingest, another data center for reports, without affecting either process. What does this look like when we introduce Kafka? So let's say we have data being created in Cassandra. Let's say this is the one Cassandra cluster, one Cassandra data center, and we want to do some streaming analytics, right? Well, we can take data out of Cassandra, use Kafka to pipe it into Kafka topics, and while Spark runs it, that the Kafka Connect can then send that data back to another data center or the same data center. And so this process could be bombarding one data center while the microservices are being powered by another data center. It's all about workload isolation. So these are logical diagrams. What people don't realize is that in order to make this happen, you're going to be potentially using separate data centers. Same thing here. You take data off of Kafka using Spark streaming, you store it into a data center here, and at the same time, you store it in this other in another key space. Okay, and you can have batch processing happening on a separate data center. All the while, right? This process being run on one data center, this process being run on another data center. All the while, this data is served up with another data center, yet another data center. So I know I've been talking in kind of abstraction, but here's an example of what that could look like. So we have a data center here where we're running Spark streaming in Spark. It takes a message off of a queue, saves it to S3 for historical purposes, does some processing, and also puts it into let's say a traditional data warehouse. Once that's done, right, the customer's key space is then replicated. Right, so message is coming, it gets processed and put into the customer key space. Customer key space is then available in two other data centers. One data center used for doing BI, while running Spark SQL, and another data center to power a REST API. So in this case, it's a DSC cluster. It doesn't have to be, but a DSC automatically synchronizes Cassandra with Solar, so you can do search APIs on here. Right, so these different data centers are running 3 different workloads. Now, it shows you that it's running Spark in all 3 data centers, but Spark here is being used for search analytics, right? Leveraging Solar and Spark together. Spark is being used here for Spark SQL, and Spark is being used here for Spark Batch and Spark Streaming. And the data, the customer's key space, is being replicated across the 3 data centers in real time. I mean, this is a real-time customer platform. Customers use a variety of different microservices. Those microservices are emitting messages saying user did this, user did that. We process it in real time, we put it here. And while that's being processed, business can do reports off of that data in real time, and the users can then get back their data as a full profile, right, in real time. Or other downstream systems can use that as a full-fledged customer 360, right, in real time. So that's only possible because we're using workload isolation. Let's combine Kafka, Spark, and Akka. So in this picture, what we see is we see Kafka getting data, right? And we use Spark streaming. And you can also use Akka to save the data to a Cassandra cluster. And what does Akka do, and what does Kafka do, and what does Spark do? Well, Kafka is being used to get data from the outside. Akka can be used for basically getting a message, doing something with it, and doing something else with it, right? And sending it off, right? Very, very lightweight actors. They're like the ultimate microservice. So if we want to just get data and dump it, we don't need Kafka for that necessarily, right? But Kafka standardizes the flow of all the data. Akka can do the lightweight processing. And anytime we have to do heavy aggregation and analysis, that's when we use Spark. So what would we do to do this physically? Well, something like this. Right? You can have Akka getting messages off of a Kafka queue, storing the data here. Spark streaming is analyzing, aggregating the data, putting it into other tables. That the data gets replicated here. And then Presto can be used to do the reports in real time. Here's a more detailed version of the same general architecture, right? So it shows you that as data is getting put into the Kafka cluster, you have Akka, doing some publishing and some stream processing, and then there's a little bit of overlap where we have Spark also doing some processing, and in this case, they're using Akka inside Spark. Spark to basically schedule it, Akka to actually do the processing, right? And then there's yet another set of Spark, which is happening using pure Spark streaming from Kafka streams and Spark batch processing. And here's Spark being used in 3 different ways. And so we would possibly do that if we can manage it, right? Do all the ingestion in one data center, use Spark streaming in one data center, and do batch processing in another data center. And I should keep repeating this, is that this data center could be bigger than these 2 because you have a particular speed requirement. Or this could be huge because there's a lot of users using it. It doesn't change the topology. We're just adding more nodes. And with Cassandra, adding more nodes automatically grows the cluster. Right? It's not a really complicated process. I don't think it's complicated. And here's another picture, right? Having data come in from Akka, like Play, which is a framework for Akka for making web applications. That sends data to Kafka, and you can use Spark streaming with Akka streams, and all that gets put into Cassandra. And so while this is happening and it's getting replicated, You can have other systems do reads and analytics processes. So I'm sorry, I realized I didn't add any resources, but we're almost at the end of the presentation. I want to do a quick recap, right? These diagrams that I'm showing you right now, this one, this one, this one, I made that one, but these three right here, this one right here, this one right here, this one right here, this one right here. Okay, all those diagrams, I didn't make those. That's out on the public internet, right? So the pattern of using Cassandra in fast big data it's very established. But the way you implement it is multiple data centers at scale. Right? Nobody shows you these diagrams, right? And so the closest thing that you'll see to that, this is on some of our public stuff, is to do it properly, to do these advanced architectures properly at scale, like the way that Apple and Netflix do it, or Spotify or Walmart. I mean, it depends. You just name some big company that are using Cassandra. To do it at scale, they're probably doing it with workload isolation. Some of them I know have separate clusters, but that's for a different reason. Okay. So that's it for my presentation today. Happy to answer any questions and have a quick discussion.
Is the process that syncs data between data centers the same as the streaming process that syncs data between nodes in Cassandra?
No, it's not the same, because streaming is basically taking SS tables and streaming the SS table. Now, I think Cassandra 4 has a slightly better engine. It's called zero copy streaming. The replication that we're talking about is when we do the write, right? It identifies where the other partitions are, and if it's a consistency all, it forces that, right? If it's a consistency less than all, right? Local quorum or whatever, it forces it to its scope, and those messages are sent to those nodes as mutations, right? So when we talk about those thread pools, the thread pools in Cassandra are like, they're just like microservices, and messages are being sent. So that's how it's actually replicated. Repair is a different way of synchronizing data. Streaming is a different way of moving data. Does that answer your question?
Yeah, that's good.
Great.
Rahul, I just want.
Yeah, go ahead.
Yeah, what I understand is Kafka, Akka, and Spark streaming. They are basically for, in the sense, main. Main goal of them is to process the streaming data, right?
Kafka streams, Akka streams, and Spark streaming is just, well, you can use it for a variety of things, okay? But it's Kafka streams specifically, it's operating on the topic itself before it does something. You need to have Kafka,
Okay.
right? Akka streams, doesn't matter. You could get the message from anywhere. You could do some processing on that stream and then send it to another stream, or even save it back to Cassandra. Same thing with Kafka streams, okay? Kafka streams, you kind of need Kafka. That's the kind of main difference, okay? And Spark streaming, similar to Akka, you don't need Kafka. You can take data from anywhere. But you don't have necessarily like a limitation. So in Akka, you're in Kafka streams, the goal is you get the data, you do something with it on the topic, you save it back to the topic, or you take it and you save it somewhere else, and you're done, right? And streams are 1, 2, 3, 1, 2, 3, 1, 2, 3. It's just an unbounded stream is an unbounded set of data coming in, right? Akka, again, you would hope to do that. Unbounded stream, you do atomic operations on each event or each message, and you do whatever you need to do, and you're done, and you go to the next one, okay? But when we're talking about Spark streaming, then the world is your oyster. You could be taking a data and doing more work, more distributed processing, because you're connected to something bigger, okay? And technically you could do that with Akka streams as well, but you have to create your own topology of Akka actors. So in each case, Kafka streams, you could do the same processing with a topology of topics and Kafka streams processors. In Akka, you could do the same thing with an Akka actor topology. In Spark, you don't have to necessarily build a topology until you absolutely have to, do lots and lots of data processing. But when you define it, it kind of does it on its own. That's the main difference. Spark does its own separation of work, whereas in Akka and in Kafka, the separation is only at an atomic level. It scales it, but it doesn't necessarily scale other types of operations.
A little more to extension to this. Again, when we are saying Spark streaming, moment we say streaming, is it goes with the distribution? No, right?
I don't. Could you repeat that question? I'm not sure what your question is.
No, when we are saying streaming, stream means it's a combined data, right? It's a not separable.
No,
No,
stream,
I'm just
yeah, stream. At least from when I talk about streams, I'm not talking about Netflix streaming. Okay.
No, I don't know.
I'm just joking. I'm just joking. When we're talking
I'm just trying to
about
understand.
streams,
Okay.
yeah. No, when we're talking about streams, it's an unbounded data set where you don't know where the end of the data is. That's a stream. That's the definition of a data stream.
Yeah. Okay. Then when we say distribution in the Spark, how it goes with?
Right. So like, let's say you have messages coming in, okay?
Yeah.
One message comes in and you need to do a machine learning operation for that, just that one message.
Okay.
I'm not talking about 50 messages being managed by 50 Spark streaming nodes. I'm talking about one message comes in, but you need to do a big job with that one message. Well, that big job can be separated in the Spark cluster for that one message.
Okay, probably.
So
okay,
Spark,
fine. I'll come back on that probably. I understand.
I think you're missing something, and I want you to understand what
probably yes. Yeah.
Yeah. Spark, as a batch processing technology, we know what it does, right? You give it a job, it does it.
Yes.
What if that job has to manage, read 50 records and do an average and save it somewhere? If you have 3 nodes, it's going to separate the work and it's going to do that, right?
Correct. Yeah.
Okay. So what if we want to have new data coming in, but only when that new data comes in to recalculate the average? Well, we would update a record, right? And send a message to Kafka. The Spark streaming will pick it up and say, oh, okay, I need to recalculate. And then it will do the same job. So nothing changed, right? It still needs to distribute the work. Okay. So Spark streaming is can be used for doing just basically commanding Spark to do the work. Doesn't matter how big the work is in Spark, right? It could be small, it could be big, it doesn't matter.
Okay.
I still don't think you're understanding it, right? So that's what I'm trying to get you to understand.
No issues. I just go. I got your points. I have taken important points there. I'll just take them as a reference. I'll go through once again.
But that's the thing. It's something simple, right? So I'm also trying to be a better communicator here, right? So it's something simple, right? You have a Spark job. You have a Spark job that runs. Okay.
Yeah.
It takes 30 minutes across 6 machines, but it only runs when you say run Spark submit. Okay.
Correct.
Okay. I now want that same Spark job to run every time there's a data that's updated.
Yeah, that can be triggered using the streaming.
With streaming. Okay.
Yeah.
Okay. So you understand that part now. That's what I mean by distribution of the work. That the actual job is getting distributed. Okay. Now, the other thing is, if you want to use something called structured streaming, that's something different. Structured streaming is where the data itself, the unbounded data set, is available as like a data frame. And you can do operations on that data frame, and then you can save it somewhere else. And in that case, you can do parallelized stream processing. similar to what we could do in, let's say, Kafka streams and Akka streams.
Okay.
Okay.
Okay. I got this point, but actually my query was, this question was to frame actual query. Okay. In the sense, now, since Kafka is also a streaming, and that we are serializing to the Akka, not serializing, I might have used the wrong word. These are going in one after the other. Okay. Means Kafka comes first, Akka comes next, then Spark streaming. Now, all these are the streaming, right? Means how we are, what to say, how we are taking advantage of each of these, what to say, tools.
Sure, sure. So Kafka streams and Akka streams, you can have a very close comparison. Okay, very, very close comparison. Kafka streams, you absolutely need Kafka. It doesn't work without Kafka, right?
Yeah, yeah.
Well, what if you're using Google PubSub Lite and you want to do stream processing?
That is totally different. Yeah.
I know that it is, but you can do similar work in Akka and Kafka stream, Akka streams and Kafka streams.
Okay.
So if you don't have Kafka, you use Akka, right? Okay. And that's a simple distinction, right? You either have Kafka or you don't. So if you have Kafka, you can use Kafka streams or you can use Akka streams. Does that make sense?
Okay.
If you don't have Kafka, you can only use Akka streams.
My question was, when we are trying to combine them, is it not possible to do it by one of means using either Kafka
both.
or Kafka, Akka or Spark streaming?
Yeah.
Or
so
using combining these things, are we getting the extra output in the sense of what to say?
Yeah.
Benefits.
Absolutely. Absolutely. And that's where in the 4 minutes, I can't explain the distinction between the architectures of Spark and Akka and Kafka. So that's a different conversation. But to put it very plainly, okay, put it very plainly, Kafka is an ecosystem of various tools. Okay. Kafka is Kafka Broker. It's Kafka Streams. It's Kafka Connect. It's KSQL. It's Kafka REST Proxy. That's Kafka. Kafka is the ecosystem, okay, around moving data.
Okay.
Right? That's one kind of like part of the Venn diagram. Okay. Spark streaming is about highly distributed stream processing combined with highly distributed just general computation. So there's operations that we can do in Spark streaming because it's Spark, right? At huge scale that we wouldn't necessarily be able to do on Kafka streams, but it's separate. Where does it meet? Well, Spark streaming does not have its own storage, but Spark streaming works with different queues, right? It works with everything else. Kafka streams, you need to have Kafka, end of story, right? So you can still use both of them together. Then the question is, where does Akka come in? Akka's purpose is to make a framework that uses what's called the actor model, which is the ultimate microservice, where every operation is just get the message, do this, and do something else, right? The speeds that you get with a properly built Akka cluster, an Akka application, it kills everything else. That's why people in the stock markets and financial world use Akka, right? So it's not necessarily one is better than the other. They're built for three different things, but one is better in terms of speed. Another one is better in terms of distributed processing. Another one is better because it has an ecosystem of other things around it, right? So it's not really apples and apples, right? We're talking about apples and oranges. So you're getting a fruit salad if you want to use all three, but it's not, you're not comparing like C++ and Java, right? It's not the same thing. Just because it has the word streaming in it doesn't mean it's the same thing. That's what I'm trying to get at. Three completely different things that can work well together or work separately. Okay.
Okay. Yeah.
All right. All right, folks, it is top of the hour. It is 1 p.m. Eastern. Good questions. Appreciate the questions. And, I think what spawns me is maybe to have a topic for data engineers lunch to compare the three things, right? Because, partially it's a fundamental knowledge of the things, right? Just seeing the title Spark Streaming is like, oh, they must all be the same. Like, no, they're not the same. They're separate tools for separate purposes. But that could be a topic for the future. Okay. All right, everybody. Thank you all for coming. We'll see you next time, next week, same time, same place. And looking forward to, also we have data engineers lunch on Mondays. So check that out. All right. Talk to you guys soon. Bye-bye.
Thanks, Raul.